Okay, welcome back. Class 2. For those of you on YouTube, like and subscribe. Hit that bell. Yeah, my son wants to be a YouTuber and he's 10, so I'm kind of like, yeah, not yet. You need to work on all the things you need to do to be a YouTuber before you can put your video and whatnot online. So he's working on, or at least slowly working on, video editing, which is something I also don't do very much. But we're trying to teach. I'm trying to learn him that. See, this is it. I've lost all my ability to speak now. So you've got an announcement today. If you haven't checked your email, they put an announcement on Icon that office hours Monday are from 1 p.m. to 3 p.m. I've got a weird travel schedule next week, and I had to move things around to make things work. Um, there's an office hours link for Outlook in there as well too. So I know you don't have to do this, but there's if you go to the UI Outlook and you want to add subscribe to that calendar, you can. That way you can tell if I change my office hours or before you show up, you can just see it in your calendar if it's there. It's not a big deal. You don't have to do that, but it's just trying to make it so that, in this environment that we live in with a lot of remote whatever, that you can know what to expect and you're not just waiting in my waiting room for me if there aren't office hours. Okay? One thing I also wanted to bring up was our class notebook site. Now, Michael seems to have discovered that it's not working well with Chrome at the moment. So if you're using Chrome, that might be something to worry about. A couple other things on here. Number one, when you load this site, right, first of all, the way you can get to it, we have a link on the course website, but if you go to notebooks.hpc.uiowa.edu, you can go down here and find our link to it as well. When you load the site, first of all, you don't have to load the site. You can just use R on your local machine just fine. Although getting the files down, if you know how to use Git, you can easily get them, but that's okay. You don't have to. Here, there's two folders here, class files and class data. Don't put anything in those folders because those folders get downloaded from GitHub. Well, class files comes from GitHub, our class course repository there. Class data, I don't know, I could have saved a data set there, but I don't think that any there. So when you see those folders, don't put anything in there because it will be overwritten the next time you sign into the folder in the server. So that also means that, for instance, today, if we go into class files, under lectures, you'll see path analysis. It is probably advisable to make a if you want to save or if you want to work in that, save your notes, just make a copy too, and then just go up to home and save it there. Everything in the home directory should not be overwritten. So that should, I'll just call this LO2 for lecture 2. That should allow you to not have to worry too much about having issues in any notes that you've taken being overwritten. But for instance, today we have our R file in the lectures folder. Questions about notebooks. Okay. Should be on the website. I think it should be there. Yeah. Yeah, right there. There we go. Yeah, I did do that. You're welcome. All right. Then the other part is today's lecture. We got a little bit of a problem. This is typical with R. Some not typical, but some of the mildly frustrating parts of it. So I use a package called SEMplot. I've been using it for like years, right? Um, I don't use it that often in my own research. Let me be real. I use it when I teach this class. I haven't taught this class since 2016. So you know where this is going, right? Some, but not all. When you try to run SEMplot to plot your diagrams, it depends on a package called OpenMX. It will not, SEMplot will not install directly in R without that. So you don't get this without, I had to troubleshoot this before last class also. When you're trying to install it, you'll see just, it failed. So track down why it failed. It failed because OpenMX, the current version of it, requires R 4.5 or higher, and IDAS Notebooks uses R 4.4.1, I think. So that is the problem with it. What we have to do is then get OpenMX to install, and I hope you have an appointment or you have your time on your hands. Because if you run this block of code, if you installed an old, so you can go and get the old version of OpenMX right here through CRAN, and to install it, you have to say repos equals null. Well, that means that you can't install its dependencies, of course. So then you've got to install its dependencies. That doesn't take very long. But running this set of lines right here, that's going to take a good 20, 30 minutes. It drives me nuts. So you may not be able to plot if you're following along in the lecture today, or you can start it now and hope it gets done by the time the lecture's over. Yeah, Michael. No. No. Once you get it installed, it should run because where it puts OpenMX, see, it just failed for me as well. It puts OpenMX and everything in this R library right here. So once it's installed, you should be okay. Just anyway. So yes, I've been trying unsuccessfully in the moments I had to get here to get this thing to run. I would then close the server window, assuming like the other notebook site for research, it stays open in the background. It hasn't. So you may not be able to plot if you're using this today. I'm going to end up having to use my local R instance. It should work on there. But again, you may not. Yeah. Yeah, I have no. Actually, I have no idea. I don't know what. Yeah, yeah, yeah. I would. I would also say that R on the virtual desktop. I guess maybe you can use. Yeah, it's just. It seems if you're going to put it up there, just put R on your local machine if you're going to use the local desktop if you can. Remote desktop. I don't know. It's up to you. I mean, you can. Your workflow is how it works. I've always found it to be somewhat slow. The R is open source at least, so you can do it. Actually, that brings up the notebook site is nice to teach from. It's nice for collaborative work, maybe. And it's nice if you have multiple machines you're running R on and you want one setup. But after that, if you have, since R is free and open source, I feel like it always runs better on your local systems. So, but there we have it. Next, last announcement. While we're sitting here, there should be, or maybe by the end of class, I can't remember where I announced it, there will be a homework this week on path analysis. So we're diving in. Homework due next Tuesday. I have come to my office hours. If you need it, A. Kyung has office hours on Monday. Erica's is Tuesday. There we go. Actually, that just reminded me. I forgot that Erica would like to make an announcement. So let me just do this. Pause the record. Thanks. And I want to tell YouTube to thank one of our students for reminding me to restarting this recording. You've only missed a few minutes of class. But that's okay. It's about what we're going to get into. And here it is. Pause YouTube now. Okay, next. Thank you very much. Yeah, I hate it when that happens and I pause and I don't continue. All right. So way back in the day, a while back, the first time I was teaching this class, I wanted a real life example. So I found a paper by Pajares and Miller in 1994 about the role of self-efficacy and self-concept beliefs in mathematical problem solving, a path analysis from the Journal of Educational Psychology. Seems really nice, right? 1994. I'm old enough to be alive then. Many of you may not be. That's okay. This paper, though, came up when I typed path analysis example. And I was like, oh, let's find out what it's about. I'm teaching in education. Educational psychology is what we used to call many of our programs. It was like psychology and ed. Now we do things like learning sciences and other things like that. This is a study of 350 undergraduates, 229 women, 121 men. And there were about 10% variables missing. I literally took the paper and just recreated the analyses based on their numbers. That's what I did, right? And then simulated data. Um, so I made 10% of the variables missing or observations within variables missing completely at random, which you probably don't really know what that is unless you study missing data. Missing completely at random is just a simple chance. It has nothing to do with your data that you've collected or didn't collect. Just literally like I flipped a coin, and if it landed heads, the data were gone. If it didn't, it did not. So I will note the simulated data characteristics differ a little bit from the actual data, particularly because of the assumptions of path analysis. So once you do a path analysis, and if you muddled through the chapter and all the matrices that was assigned, what you can see is you can go from coefficients to a distribution for data through great difficulty, but you can do it. But that distribution has some assumptions. And we talked a little bit about this last time in the context of what a generalized model is for. But particularly, a lot of the variables that were in this data set had bounds to them, like a 20-item math assessment. Right? Ranges score from 0 to 20, of course, summed up items. Some variables had boundaries that the simulated data exceeded. I didn't change that. So missing data and boundaries, some of the assumptions will cause some of the results to be different. So if you pull that paper down, you'll see some of the results are a little bit different. Anyway, that's not a knock on the paper. That's not me claiming anything about it. There is one sign difference that's a little bit weird that makes me think there might have been a typo in one of the tables or a typo in my code, but I'm not claiming that there's a problem. Right? Here are the variables from the paper. We have gender, which we now would call sex, biological sex of a person, male or female. We have math self-efficacy, which is a report, self-report, so how strong you feel at mathematics, how well you feel, how capable you feel at doing math. We have the perceived usefulness of mathematics, another self-report. Survey, how useful do you think math is? I should ask this question, how useful do you think SEM is, right? Same thing. Math anxiety, which is clearly another scale. Reliability ranges from 0.86 to zero point 0.9. Math self-confidence. So math anxiety, how much does math make you anxious? Math self-concept, I don't really know what that means and why that's different than self-efficacy, but your self-concept of how you do math, I'm an aspiring mathematician, or I can't do any of it. I've been on both sides of it, to be honest with you. Then we have prior experience at the high school level, the number of years of courses in high school which students took math. Prior experience at the college level, which is the credit hours students took. And then finally, math performance. So this is a 18-item multiple choice test altogether. And might you be thinking to yourself, wait a minute, last week you just told me we had this example that said you shouldn't add things up. All of these are sum scores, with the exception of number of years and number of credits, right? I guess those are sum scores too, but they're counts, right? And this is clearly violating some of the assumptions that we talk about. Each of these variables is not perfectly reliable. Yes, that is what happens, unfortunately. The remedy to this is a full-blown structural equation model, but the information to do that was not in the paper. So all I have is the paper, so that's what we have. So this is going to be our path analysis example. Okay? Again, in reality, here's the path diagram. Each one of these boxes over here to the right of the screen, each one of those should be circles with indicator variables for each in a path analysis. But we're going to add them up and put them all on this metric. That's what we tend to do anyway. It's an assumption that, as you saw last time, will make us think that we have more precision in our analysis than we really do. How are we doing so far? This is where we're headed. This is the path model that they talked about, right? So once again, the boxes here represent observed variables in a convention that we use in the structural equation modeling literature. Now, again, if you're in directed acyclic graphland and causal inference, or you're in Bayesian inference networks and other parts of education, they don't really make a distinction for the variables with circles or squares or triangles even, but SEM likes their shapes, and so here we have a bunch of rectangles. A quadrilateral, what should we call that? A parallelogram, a rectangle of some sort represents anything with 90-degree angles. Let's just put it that way. And this is my, here I am with my math self-concept. Anything with 90-degree angles in SEM represents an observed variable. And so when you add things up and you don't make this a measurement model, we're treating it as if it were observed. And similarly, that it has perfect reliability unless you do something to fix that. Okay? So each of these is going to be treated as an observed variable. Again, a structural equation model, what I like to call, I'm using the definition of one of my mentors, Rod McDonald, is this path model where we might have some of these be measured variables, measurement models, right? Latent variables, right? We're ultimately interested in this, but what gets in the way is unreliability for some of our constructs and scales. Okay? All right, so in this example here, the red arrows represent what we call direct effects, right? And the direct effect in the diagram is basically if you were to go take a set of equations, you could make an equation where each of the rectangles that has at least one arrow terminating at it, each one of those is a dependent variable, right? So in this case, we have 1, 2, 3, 4, 5, 6 dependent variables. You could think about writing 6 regression lines When you do that, this direct effect represents the slope of the variable that's predicting that outcome, right? So this line connecting high school math to math performance would be the slope for every 1 unit change in high school math. This is the amount of change in math performance. But now, because there's more than one variable predicting it, that'd be holding each of these constant. That's what we'd say as well, like a multiple regression. We basically call that, right? So any one box here that has multiple arrows is like a multiple regression, but we want to do this all simultaneously, right? So those are direct effects. Additionally, you might see other indicators here, something called residual variance. So when every time you have a linear regression, at the end of that regression equation, there's an E, and that E has a normal distribution with some amount of variance to it. We call that a residual variance, right? What's left over of the variable that's not explained by the regression. That's usually denoted in path diagrams with some type of potentially arrow, some types of double-sided arrow, some types of there's 3 or 4 different conventions in the path analysis world to do this, but it does represent what's left over. That's the path diagram description. How are we doing? That's where we're headed, but we're not going to start there. So what I really want to do is back up just a bit. I got to give you a little bit more of the mathematics, right? And I have a true story for you. Yes, Michael's cheering. I went to the dentist in Athens, Georgia, when I used to live there, and polite person making small talk. What do you do? Oh, I teach. I'm a professor. Great. What do you teach? Statistics. And she says, "Oh, I totally get that. I bet people feel about you like they feel about me." I'm like, "What do you mean?" They don't want to see you. Pretty much, right? But that's it. I have to go through this right now because I want to have a conceptual understanding. When you get a little bit into the path analysis world, things start to look a little different. Well, we talked last week about things being different just because we use this maximum likelihood thing, right? Linear models don't have ANOVA tables anymore unless we really have to work to get them. We have these weird hypothesis tests by the names of likelihood ratio or walled or even score, right? With path analyses, we also have a bunch of other things called model fit statistics. We'll talk about those today as well. And the type of model fit statistics, where this really comes from, is the assumptions of all of the variables put together at once, right? So what I mean by that is, if you look at this not as, and again, just take the dependent variables here. So there's 6 variables, everything but this one here, gender, okay? Everything else. If you look at all 6 of these, what a path model has to do is to recover a distribution of 6 variables simultaneously, right? And that distribution is important because if a model doesn't fit the data, it does a really poor job in representing what the data structure looks like that you have. So with 6 variables, a distribution that we often use is something called a multivariate normal distribution, right? In path analysis. A normal distribution, you've seen that before, the bell curve. Multivariate means a bell curve in multiple dimensions. Let's see if I can draw. It's always dangerous, but you have, your unidimensional bell curve here. If we call this x, f of x right here would be the 0. There's 0 right there. Oh gosh, give me the object eraser. There it is. There it is. All right. So here in a normal distribution, right, you can talk about this is the curve, and the height of the curve is sort of the relative frequency. So the mean is the most relatively frequent. Everything else is not. The units, the height of the curve, are not really meaningful in a continuous distribution in an absolute sense. They're really a relative sense. In multivariate normal distribution, this is fun. There we go. Turn that off. Multivariate normal. Let's see if I can do this. Michael, you teach math, right? There's X. There's Y. Actually, nope. That should be Z. Already messing this up. Let's call that Y. I want that to be Z right there, right? A multivariate normal distribution just looks like basically a bell, right? A 3-dimensional bell in 3 dimensions, right? Yeah. Good luck with that, right? 4 would have we'd be stuck there. We have 6 variables, right? And the key that I want to talk about is this multivariate normal distribution itself has two sets of parameters. You already know them, but they talked about just a little bit differently when you get to multivariate. Um, each variable has a mean, right? And in univariate normal distribution, you knew that. The two, let me back up to this. Let's recreate our drawing. Let's do that. Get out of here. The univariate normal, we recognize the mean, the center of it, as our mean, and we can talk about how much variability as our variance, right? Sigma squared. So those are the two parameters that characterize the shape of the normal curve, right? So for the multivariate normal distribution, a similar thing happens. Now instead of having one mean, though, in this drawing we'll have two, right? So each variable will have a mean. Instead of having one standard deviation, so one for x, we'll have two, one for x and one for y. Right, remember, z is just our density, how relatively likely now a pair of observations happens to be. Now, there's one other parameter in this that we don't often talk about, and that's the covariance between x and y. Right? You may have heard of covariance, depending on how much statistics you get. When I was taking statistics, it was like you take your intro class, linear models, linear regression. Yeah, there's someone says covariance once or twice at the end, right? And then you jump into multivariate world, whether that's in path analysis or otherwise, and it's everywhere, right? So a covariance is basically a rescaled correlation, right? In fact, the covariance, you can even see this, the covariance of two variables, x and y, is equal to, the correlation between x and y, not the covariance, correlation, right, is the covariance of x and y divided by the standard deviation of x and the standard deviation of y. Okay, so let's unpack this. Correlation ranges between -1 and 1. We know and love it. It's a standardized unit. It's your first standardized coefficient. The covariance is like that, but what happens is covariances have units attached. If you remember, I mean, if you took, well, you're a chemistry major, right? I remember this. I always do a chemistry example, so tell me how good I'm doing at teaching chemistry. Now, I have a big fat F in chemistry in high school. I did. And then I took it in college and I got A's, but that's all right. High school was a different time. But I remember this unit called stoichiometry where we had to cancel units. Think of it this way. Covariance is reported in units of the x times units of y. So if x is height in centimeters and y is weight in kilograms, the covariance between x and y would be in centimeter kilograms. That sounds weird. That's why we don't use it, because centimeters has a certain scale, kilograms has a certain scale, and their product has yet another scale, and it's really hard to use. But covariance, the unit that we talk about, a standard unit, is characterized by a standard deviation. So standard deviation is effectively like the units of x, and standard deviation for y is the units of y. So this is my stoichiometry, terrible chemistry example. We take covariance and we remove the units of x, we remove the units of y, and we're left with correlation. So put another way, correlation is really understandable, and it measures association. Covariance is not at all understandable what it means, but it measures association as well. It's basically the same measure, just rescaled into units. Okay? So covariances show up in multivariate normal distributions. And the way that we usually show that is in a matrix, like a correlation matrix. That's a covariance matrix. The covariance matrix along its diagonal is, first of all, it's square and symmetric, right? Correlation matrices, square, right? Number of variables in the rows, number of variables in the columns. Covariance is the same way. Number of variables for rows, number of variables for the columns. Each element of it represents the covariance of of the variable for the row and the variable for the column, right? So if I have, going back here, this covariance matrix, often we denote covariance matrices with a sigma. I usually, for a matrix, I put a little half arrow over mine because I learned calculus from that way. The covariance matrix will have the variance of x and the variance of y down the diagonal, and the off diagonal will have the covariance itself. Now these off diagonal terms, these two are equal. Right? So it's a square symmetric matrix. The diagonals are the variances, the off diagonals are the covariances. Yes. This book will only be talking about a triangular version of this matrix here. That's right. So a triangular matrix, yes, is a matrix that's formed by taking the diagonal and what's ever below it or what's ever above it. And the rationale for that is this unique the extent of unique elements in the matrix. Okay? So those are all the things. So if you look at this covariance matrix, it looks like there's four parameters, but we only have three to estimate, right? Because this one is repeated. But the triangular matrix would only be that part right there, and often the upper part there's zeros. Other way around otherwise. But there are other triangular matrices, and they do show up in statistics a lot. Depending on where you learn linear models, you'll learn about certain factorizations. Have you heard of QR? Probably haven't heard that before. Or LU, or Cholesky. Michael probably knows Cholesky. Oh, anyway, the wonders of matrix algebra. See, it's like going to the dentist. I haven't even made it through two bullets yet. So why I'm saying this right now is when we have a path model that looks like this right here, where all of the dependent variables, which I'm going to call endogenous variables in just a moment, all of these are continuous, then the assumption of multivariate normality is made. So that means for this, we would be thinking about all these variables have a six-dimensional distribution. Each one has a mean and a variance. And then there are, and I don't know how to do the combinatorics in my head, but six choose two covariances, right? Every pair of variables has a covariance, right? So each one has a covariance. So to characterize the distribution of the data, a multivariate normal distribution is used. Why that's important is because that multivariate normal distribution gives us a lot of benefits when it comes to evaluating model fit. Multivariate normal distributions have always been one of the first statistical distributions to work with. You may not believe this if you look at their distribution function. They're actually relatively easy to work with. I put the relative there because you can do certain math tricks to them to make them a little bit easier to see what's in them. Math tricks meaning take a log. Taking a log of it makes it a little bit easier mathematically to work with. That doesn't mean it's easy, and doesn't mean I'm going to go and prove it to you how easy it is by standing up here and just the top of my head. Okay, so this covariance matrix is the core of what we're trying to understand if our model fits our data, though, right? Because if our model fits our data, then if we were to go and take our model parameters from this and generate data with them, that data that we generate should have a covariance matrix that is close in value to the covariance matrix we have in our data. But if we do that, we generate data from this and compare, and it's not close, there's a problem. It's called model fit. And that's one of the big differences between univariate linear models, like linear regression or ANOVA, and multivariate, like path analysis or multivariate regression, is that in the multivariate sense, we have to basically ensure our model also provides what the covariances are. And because if it doesn't, we've got an issue with how accurate our parameter estimates are. The word bias shows up. Bias in the statistical sense means inaccurate, not close to its true value. Okay? So that's where I'm going with this. Sorry to take you to the dentist's office. I get to go to the dentist on September 15th. So I know. All right. So much like multivariate ANOVA, multi-level models, what we have to do is find an approximation to the covariance matrix. So we build this path model. The path model should approximate the covariance matrix. Well, there is an art to it, though, because you sort of have a model building process. You build a model, you check its fit. If it doesn't fit, you make, now this is where in other parts of statistics, we might call it the garden of forking paths. We have to make decisions about how to change the model to improve its model fit. We start getting into capitalizing on chance, p-hacking ideas, but part of it is you do have to establish good model fit. And you have to describe the process in which it goes into. That's funny. You didn't get to hear this, and I don't know if you hear this on YouTube, but when you flip the transition, I have a Law and Order chime. Remember Law and Order? You can't hear that. Trying to hope. I was hoping that maybe you could hear it, get some joy in your life instead of the dentist. You just hear Law and Order. No, it's not. I'm hearing it in my ear. So those of you on YouTube may be hearing it as well. Actually, no, I've cut the volume off from coming from the video. So trust me on this one. It's amazing in one of my ears. This is cool. All right, let's build to the path analysis, but let's do so on one step from where you might have learned already, which is let's take the mathematics performance and the perceived usefulness. Let's take two variables and predict them simultaneously. Okay. We will assume these to be continuous. Remember, that's a tenuous assumption, potentially, right? Certainly, math performance, that's a score between 0 and 18 on a math test. Um, and initially, we're going to look at an empty model with these two variables. Empty model again, like we talked about last time, or like you talked about in linear models, is our baseline. It helps account for how much variance is in each, what the covariance is. And this is how it works. Here we have two regression lines. We've got performance, we've got usefulness. For each regression, there's an intercept and an error term. Now you'll note I've had to superscript the words for each variable because when we have more than one regression at once, we have more than one intercept. And if I would have left that off, it'd be ambiguous, or we would be assuming that the intercept is the same for both. But we know, I don't know what the scale of use is off the top of my head, but I know performance is between 0 and 18. And when we fit this model, both of these are going to be each of the respective variables means. I can't imagine that usefulness will have the same mean as performance, right? It's an unnecessary constraint. So those two variables, when we put that in, what we are describing here is two different regressions at once. Now the error terms you knew before to be univariate normally distributed, but now we have two. So that's where we have this multivariate normal distribution to consider. We often notate a normal multivariate normal almost like a normal. You may have seen normal distribution notation before where we describe a variable as, let's say x, we have a tilde follows normal with some mean and some variance. You've seen that before, right? Sort of normal, two of these. Multivariate normal works similarly. We have these two variables. It's multivariate normal. The mean for each set to 0, so that that bold and capitalized, well, just bold numeric right here represents a 0 vector. That's an important term in matrix algebra, a vector full of zeros. This covariance matrix, which I'm calling R here, I had mirrored this off of SAS proc mix. I was trying to connect path models to mixed models previously. I'll get there in just a moment. This covariance matrix now, though, the diagonal of it has the variance for each respective variable. So performance in the top left, usefulness in the top bottom right, and then the covariance between the two shows up in the off diagonal. And remember, these are the same values. Question. Perfect. So these are error terms. So if you just, I don't want to complicate the multivariate normal. The same thing would happen with a univariate normal. If you set the mean to something other than 0, when we go and estimate this equation, what happens to the intercept is that it gets shifted by that mean, right? Because what we'll end up getting is the mean back from this equation. But if we set this mean of errors to something other than that, the sum of this side has to be its mean. Mean of the error. That's right. That's right. And in a model where you have predictors, this doesn't have predictors, but in a model where you have predictors, that would be what's left over for each variable respectively after you've predicted both for each person. Thank you for the question. Yes. That's right. I put the two there just to say it's two dimensions. It's often omitted, but I wanted to be clear that this was something different than our normal from before. So that's where that showed up. Thank you for the question. Um, okay, so each error term has its own variance still, right? But now there's a covariance between the error terms itself. Okay, how are we doing so far? So good. We can do this with matrices. I'm going to quickly just say, I'll skip this. I need to do that. I don't want to do that. So I had built these slides. So when I used to teach this class, I built a lot more from the multivariate normal perspective, and I'm not doing it this time. And for me, that's like riding a bike for the first time without training wheels. I have to admit, I'm sorry. I know I'm. My name is Jonathan. I'm 48 years old, and I'm teaching without matrices. But it's tough. But I'm going to get through it. I promise. Um, but I don't think it adds to this lecture, and I don't use much for it. But this is really what I was going to say. That previous slide, when you work through the math of it, what we're really saying that model is assuming about our data, right? We look at this here. What are we assuming? Well, beta zero we know from an empty model will be the mean of performance. Beta zero for usefulness will be the mean of usefulness. The variance of error for performance, because it's not being predicted, will just be the variance of performance. Similarly, the variance of usefulness. And the covariance will be the covariance between the two. So what that means is if we put it together and we say, what do we expect the mean of our data to be? It would be the mean of each of our predicted values, the model for the means for each of the variables. And that's what this is saying here. So we expect performance and usefulness to follow this multivariate normal distribution, where the mean of each is its variable, like that you would find if you were to analyze each separately. The variances of each would be like you would find if you had analyzed each separately. But then you have this covariance between the two. So what this model is implying about our data is we should have this two-dimensional normal distribution, and that should, you can almost map that to this distribution right here if we had performance and usefulness as x and y. And of course, I had just removed my drawing on it. There we go. How are we doing? I know this is a lot, except for the dentist. I'm going to put numbers in, and I'm using this to structure why we have model fit. But if we want to estimate this model, I have the Lavon syntax here. So in the Lavon syntax, what we have to do is we open and close a quote, right? So our Lavon syntax is just a character string. Much like if you've used M plus before, you type all of your code into a text file, or your R script is all in a text file. In Lavon, it's a text file. The commands in Lavon, if you put a pound symbol or hashtag in front of something, that's not a hashtag variances. Actually, you can't search that on whatever you like to search it on. But you can note that that's a comment like an R, right? So you can put comments in your code. So here, variances, covariances, and means, basically the Lavon syntax has a way to specify every one of those parts. And this is the point of what I'm trying to get at. Here's the distributional assumption at the top, right? The two means, the variances, the covariances. So we have 1, 2, 3, 4, 5 parameters we have to go and specify. In Lavon, we can specify a variance using a double tilde, right? Weird. Yeah, absolutely. Oh, I'm so sorry about that. Sorry about that. So let's do it this way. How many parameters for performance? We've got a mean and a variance. So there's two. For usefulness, we've got a mean and a variance. That's 4. And then we have this covariance. That's 5. Right? So what I'm trying to do here, why I'm doing this, why I had to take you to the dentist to talk about this, is I wanted to tie the Lavon syntax to every portion of where those parameters show up. And the reason for that is when we start building the full complicated model is if we're off on that term, there's a remedy somewhere in syntax specific to that term that you can add. Yes. Yes. Oh, I'm sorry, what's the name of what? Oh, these right here. These are the variances or the residual variance of each. Yep, yep. Yeah, in a non-empty model, they would be the residual variances. But for this, because it's empty, it's just the variance of each variable. Thank you for the question. I'm sorry I didn't fully. I've got one. I'm not. I hear the law and order. I'm hearing law and order in my head. It's like I'm going crazy. Did I see another question before I go? Yeah. Hmm? If you wanted to set a covariance to 0, you would take this term right here and implement something in syntax. Or, depending on the default options of the software you're using, you would omit this and it would be not estimated. And that is part of what's happening. I'm kind of give you like the what I want to do, because I feel like a lot of the syntax gets so divorced from where the data go that I'm trying to like tie, hey, this is what our model assumes, and these are the parts of each of that that you can go access through syntax. Because when it goes awry, there are measures you can find for each of those places, and you can see how far off they happen to be, and that's where you can fix it. That answer? Great. Thank you. Okay, how we doing? We're almost a break. 3 minutes. 3 minutes. We can do this, right? Okay, no drill at this dentist either. Although I wish it was like the sedation dentistry. Like if you could have sedation statistics, that would be great, wouldn't it? Okay, maybe not. So that's what happens when you leave the stat conference afterwards at happy hour at sedation statistics, right? Never mind. I'm trying over here. Okay, and I'm wildly optimistic that I can make it through this lecture, and that has implication for homework that we'll talk about later. Okay, so again, double tilde represents a variance. Now, it's a variance of what, right? So it's parameter on one side with the parameter on the other. So perf double tilde perf represents the variance of performance, or, and you'll note in covariance, it's also double tilde. Turns out a covariance of a variable with itself is a variance. Does that make sense? Pardon me? What's that? No, it wouldn't. So in a standardized sense, like in a if we standardize it, it'd be one, right? But because, well, I can. Do you want more? I can give you more detail if you'd like. Okay. Okay. If you look at the formula for variance, I'll just say there's a sum of x minus its mean squared, right? Here, I'm just going to tell it to you. Sorry, I have to. I can't help I can't help myself, and I want to teach. This is what I'm here for, right? Um, if you look at the covariance form, actually the covariance formula, so we'll call this x, y, x, and y. The numerator of it is x minus its mean times y minus its mean, right? And I believe this is depending on how you're doing it over n or n minus one. Okay. So what happens to this formula when you substitute y with x? You end up getting the sum of x minus its mean squared over n, which is the formula for x's variance. So that's where that happens. So covariance of a variable with itself is a variance. And so that means the double tilde means anything in the covariance matrix, really, right? And when you put performance on one side and performance on the other, you're referring to the top left variance. Or if you put performance on one side and usefulness on the other, you're referring to the only off diagonal element that's estimable here, right? And there's only one. All right, so that's the double tilde. The means, so the single tilde is mean, but it actually is model for the means, right? As Lisa would say. And many of you had Lisa. I don't know if all of you have, but most of you have. Why I mean that is when we start to build our regression itself, this is where our fixed effects, our predictors are going to go into the means section. Okay. At that note, we're at break time. Oh, question, and I'll take break. Covariance can absolutely be negative. Yes. Variants have to be positive, but covariances are bounded. Not in a mathematical sense, but in an assumptional sense. So for this multivariate normal, this for those of you who don't do math, you're going to hear womp womp womp. Just this is not something that's on the exam. I'll put it that way. I have to say that all the time now too. But this is more for your information. When you make this assumption, you assume that this matrix is positive semi-definite. By positive semi-definite in matrix algebra for a square symmetric matrix, that means its determinant is 0 or greater. Most of the time we want it to be greater than 0, and most of the time we just call it positive definite. The reason for that is in a multivariate normal likelihood, we have to take an inverse. And a matrix, by definition, a matrix is positive definite is invertible. And so for this data to follow a multivariate normal, we have to have an invertible matrix. for where it goes. So what that means is, if you remember the covariance and the formula I had before for correlation to covariance, correlation is bounded between 0 and 1, right? So that means that covariance cannot be bigger than the product of the standard deviations, and it cannot be less than -1 times the product of the standard deviations for that to happen. That's the indirect way of saying it. So I hope that answers your question. I like this. This is keeping me on my toes. I like your questions. All right. For those of you who don't care about math, welcome back. That's not true. That's not true. I'd like to take you and your love of what current value of love of math you have and expand it to wherever it may go. But I don't want you to be turned off by or turned down by or listen, just tune out. But at this point, let's take a break for 10 minutes. Come back about at 32 past, and we will start the fun again. Welcome back. Okay, had a great question in between the break there about the path diagram. First of all, you might notice in this diagram that there are two ultimate um, outcomes. When I say two ultimate, I don't. There's not a real term for it. They're all if in a path model, and I'm going to get to this in slides in just a bit. We make a distinction. There's things called exogenous variables, things called endogenous. Exogenous variables are variables not predicted by anything. They are thought to vary, hence the word variable, but they vary without explanation. They just happen to be varies. They vary, right? Endogenous variables are any variable that's being predicted, so any variable with an arrow to it. Now you'll note these are endogenous variables that aren't predicting anything else, right? So that's sort of the terminus, the terminating point of this idea. And if we walk through sort of the logic in building this, I don't really have, if you can read the paper, but let's just sort of mildly speculate like we were studying this, right? Our goal is trying to figure out why people do well in math and why people believe math to be useful, right? And let me tell you, I lived in the 1990s. Keep joking about that. STEM education has come a long way since the 1990s. Let's put it that way, right? And so was really big in the 1990s. Certainly as big as it is today, but we've learned a lot in the time. So you're thinking, okay, what could possibly impact someone's performance and perceived usefulness? So let's map this out. They're saying, oh, gender. Okay, so I'm guessing there's some type of gender norm. How different genders might be thought that think that math might be important, or how they're taught. There's a stereotype in the 1980s of the Barbie that would say math is hard, right? The girl toys that play with this, right? So, for instance, there are these gender expectations, which I hope are better. We're better off today. Let's put it that way, where we don't, it doesn't make a difference what your chromosomes or how you identify yourself as to whether you learn about mathematical symbols. Seems to make sense. But that's why gender's there. But then how much math have you taken, both in high school and college, right? So that's sort of they start. And they thought, okay, so yeah, those all have a role on math performance and perceived usefulness, but that role is not really a direct role. It's kind of an indirect role, right? And that's what this is saying. Okay, yeah, high school math performance, there is a direct effect here. So that's the only direct effect from these first variables on it. So what they are saying is, okay, your experience in math and your gender, that's almost like a proxy for the relativeness of your gender and gender expectations, impact directly how well you believe you can do math. That's math self-efficacy. And math self-concept, which is, I believe, how well you view yourself as a mathematician. And those two terms have direct effects on whether you can succeed in mathematics, at least on this one test, and whether you believe math is useful. So that is the sort of what the path diagram is saying. You hear me talking about it in this story. There's direct impact and there's indirect. So these indirect variables, we would say, mediate the relationship between your math experience and your gender and how well you do on the tests and whether you think math is useful. But more to another question that came up during the break, you'll note there's no assumed relationship between either of these outcomes, right? And that seems somewhat implausible. Pardon? It is still a recursive. This is a non-recursive. Yeah, there's no loop, so we're still one direction. Like there's no way. Like if you If you follow trace the lines, there's no way to go back to start. That's the distinction for me, at least. Um, but here, there is no relationship, right? You would think that math, if you perceive math to be more useful, you might do better at math, at the very least, right? There's another path that I didn't put on here that you'll see in a little bit, a two-headed arrow, which describes, hey, these things covary or are correlated. Or once we're done predicting them, what's left over will be correlated, residual correlation. Yeah. It would actually, you would, so it's interesting. Technically, between the two variables, yes, but that is one where we don't, and that's why that the questions at the end had the residual, whether it's residual or not. Um, when it's between two variables limited to one section of the analysis, it's not really. I don't believe it to be that way. Yeah, that's how I would look at it. There's no way to get back. The way I think of it this way is, apart from that set that have the pair, there's no way to get anywhere after. Like if you follow yourself, if this were some weird map you're taking, you'd never be able to get back to the start because all these are one-way streets, effectively, right? Yeah, that's it. These are one-way streets. There. How we doing? Did that help? Great. And there I heard the law and order thing again. My goodness. Okay, so I don't usually work with the sound on at my computer, so I didn't even know it was there. But here, like you wouldn't know because it's not here. All right, going back here, I just wanted to show the Lavon syntax. One thing I did also note I tried to change this in every slide subsequently, but this is actually model 00 for us in this lecture in the syntax, and it's right here in code in R as well too. So if you're following along in R, it's just a text object right here. And again, I'm in my local R window because I haven't yet gotten OpenMX to install on the server. Okay, so this is a bit of, but okay, so once again, what we talked about before, the double tilde represents something to do with the covariance matrix, right? Variables on either side of that represent the diagonal. And if variables change from either side, that's the off diagonal. There are quicker ways to write this syntax. I'm not using them for you right now, just to sort of slowly introduce all the parts. It's complicated, right? And then the means represent the mean vector. And later on, it's first of all, it's single tilde. And second, later on, we're going to add predictors to our model on these lines right here. So far, so good, I hope. Questions? Okay. So we can go and estimate this now. So when you do this in this model 00 syntax, if you're using Lavon, the code that you see is just an R character object. So if you can just type it in, it just looks like a bunch of characters. When you type it in the code, the /n represents your space command or your next line command. And if you put the word cat, the function cat around there, it will remove them. So just put them back. Right? So it's character. How you run Lavon, there's a function called SEM. There's actually several functions in Lavon, CFA, SEM, Lavon. Each one of them makes a few assumptions about what happens in your model and in your data. And I will go through that as we go through class. But for right now, we're going to stay with SEM. The first argument that you give it, I didn't name it, but it's literally your model syntax right here, model 00. So that's that text you created. You tell it the data set that you'd like to use. I'm using Mimic M plus because many of you may want to use M plus. I don't actually have M plus code for this class, but there will be M plus code coming along. This is to sort of make the results comparable. Fixed X equals true, I'll talk about later. An estimator equals MLR, I'll touch on briefly right now, but not say a whole lot. This is a robust version of maximum likelihood. And when you hear robust in statistics, we're not talking about flavor or aroma like you think about with coffee or I don't know what else, whatever robust shows up in English. What's that wine? Yeah, it's not. This is not a nice red wine that we're talking about. This is robust means robust to a few violated assumptions, particularly how thick the tails are in the normal distribution. So this is supposed to protect you a little bit from data that might be a little lepto or platykurtic. I remember those terms from a long time ago. Too thick or too thin tails compared to what a normal distribution is taught to say. So you run it, and yes, I have two cases where everything is empty and missing, so it'll warn you about that. And then you take your result and stick it in the summary function, and I add to it an option called fit.measures. That's something that Levon adds in. That is a way to assess model fit. So when I do that, one of the nice things about Levon is that it does a very nice job organizing your output. It's voluminous, right? There's a lot of numbers here. And guess what? We're going to learn all of them. Hooray. The good news is you learn all these for path analysis. They stick around for all the other measurement models as well, too, at least in Levon. When you start getting a little bit outside of the multivariate normal family or things that could be considered multivariate normal with some trick, these numbers go away. But we're not going to get outside of that in this class. I have other versions of class online that you can find if you'd like to go and look at that. But the key part of it is under the parameter estimates section right here. And under parameter estimates, thankfully, it separates this into different groups. We have the covariance, right? So that's that term of the off diagonal of 6.847. Each outcomes intercept, right? 13.959 for performance. So that means on average, students got about 14 out of the 18 questions right on the math test. 52.44 for usefulness. I don't know what the scale of it was. I'm sorry, I don't have that. And then we have also our estimate of variance as well, too. So that's Levon. That's how it works. And that's your first multivariate model we've seen. How are we doing? Questions on any of this? Yes. Yes, it'd be nice. So as we go on, I will add an option to that for standardized. Let me see if I can find it. There it is. Okay, the option is standardized equals true. It was about whether we need standardized versions. Is that the question? Once again, just make sure I didn't. I'm trying not to be a politician. You ever heard that saying? The politicians answer the questions that they want to answer, not the questions that you ask. I'm trying not to do that as a teacher. It's not good for instruction. But here, if we add that standardized equals true to the output, it adds a few columns, the parameters themselves. I will cover this, what each of these means in just a bit later in class. But the one to look at now is std.all. std.all, here's your clue. The variance of one, that's a standardized, when we call a standard normal distribution has a variance of one or a standard deviation of one, that's the clue right there. The std.all for the covariance, that thing's the correlation. So correlation is a standardized covariance. Okay? How we doing? Interesting stuff? And here you thought you were at the dentist, right? You do. I have a love-hate relationship with the dentist. I'm glad there are people who like it. I just find it weird. They're like up in my space and like they're clean. They're putting things in my teeth that I normally don't do. No, I do take care of my teeth. I promise. But like the pick and all that. Yeah, yeah. But clearly, dentistry is an important profession because when you need a dentist, you need a dentist. And yes, then I like the dentist, right? It's deciding how much I need the dentist, right? Okay, I'll leave this for now. I will also note, you may say, why aren't you talking about the standardized means? Because that gets a little weird in the formula for standardization. So just hold that aside for a moment as well. Too. Okay, next. Yes. So this is actually plotting the shape of what the model thinks the data look like. All right. You like that plot? Is that a good look or no? I think I got this. Well, I built this in R. It was a surface package. Yeah, there we go. So that's what this looks like. This shape right here is a multivariate normal. We've got usefulness dimension on one side, performance on another, and then this doesn't. We wouldn't normally plot this. I'm only doing this to connect model to assumption, right? If you were to fly over that mountain, right? If this were a mountain. Now, I'm clearly not a hiker, and I think I failed Boy Scouts also. But back in the day, there was a thing I remember looking at, like contour maps. Have you ever seen those? Right, where equal elevation is noted, or if you're into weather, you'll see contour maps about equal barometric pressure or whatever. This is a contour map of equal likelihood on that density, right? So these lines represent the same height on the relative frequency of the multivariate normal. So if you fly over the top of that mountain, this is the peak, right in the center. And as you go further and further out, the height comes down, right? And I overlaid that because the circles are the theoretical idea of what multivariate normal should be, right? That is the theoretical distribution with centered at the mean vector that we just estimated with the appropriate variances and covariance. And the dots are our data. So this is a sense of trying to get you to think about, we have a whole lot of like that Levon output you saw, like the first 15 pages, it seemed like 15 pages of output was basically to go and give you a numeric characterization of what you see right here. Does your model, the circles, fit your data, the dots? Yes. Yes. So I framed it as what? Yeah. So multivariate normal is our assumption. And what we have to do is make sure our assumption's valid, basically. That's the key. Um, Valid in certain ways. But I'm going to get more into that as we keep going on. But the key in all this, why multivariate normal is our friend in this situation, is we can get a plot. It's again we have two dimensions, so we can plot where our observations are and where the distribution is. That's what the point of this one is. But we normally don't do this. In fact, once we get to the six dimensional model, we could take pairs of variables, but that wouldn't tell us the whole distribution, right? Okay, no law and order this time. How we questions, comments, concerns? Taking the rust off. Like I said, I haven't taught this since 2016. Yeah, to get back to it. Okay, so this sets up the discussion of, again, probably the biggest change between what you do in linear models and multivariate, anything where you have more than one outcome, it's model fit, right? And this plot that you saw here, I'm saying this is model fit, right? The dots are what you observe, the circles are what the data should be, where they should be. And I don't know if this is good or bad, right? Because in theory, we could still make circles further and further out, right? So we have this. We could probably do a little bit more math and talk about how many observations we expect to be outside this or whatever. The bigger picture is, you're looking for sort of gross level mismatch, right? For instance, if we assume the covariance was zero in these data, oh, actually, would you like to see what it looks like real quick? You want there? Oh, there. Let's do this. Uh, so I'm setting it to zero in my code to make the plot here. Oops. There. So that's my plot when the covariance is zero. It's hard to see it because the graph is distorted. If I made this an actual rectangle, a square, not a rectangle, the hallmark of a zero correlation in multivariate normal are these concentric circles that are just not elliptical, right? Just like you think about a scatter plot of your data, a zero correlation is a circle, basically. The same thing happens in the multivariate normal. The higher the correlation, the more these turn into ellipses, right? And so I just set it to zero to look like that. You may be saying, isn't that sort of arbitrary? What happens if you estimate it to zero? Well, I can do that too. I can do this. Oops. Oh, of course. Watch this. That's what I need to do. The zero has to go in the front, not the back. Now I don't know that the back one. I don't remember right now. Yeah, that's one I'll have to punt on. But you can see actually none of the other estimates have changed in this, right? And that's because multivariate normal has a really interesting property. Well, first of all, one, this doesn't impact the means. The covariance in the means and multivariate normal are independent, which is a weird property you don't think too much about unless you're me. But then you're like, wait a minute, that actually matters. But here, um, it would have been zero otherwise. So basically, that plot I just did by setting it to zero is what it looks like. But decidedly, that's the question. If you fit the model, assuming it's zero, it looks like this. The other thing you'll note when I assumed it was zero, I have a whole bunch more numbers in this to check for model fit, and that's what we're covering right now. These numbers will take the place of us looking at the plot and trying to say, yeah, that looks pretty good. Make it this terrible statistics Rorschach test or whatever, right? Like, I'm talking about is that Rorschach where you've got an ink blot and you're trying to like see what you, yeah, it looks like a bad model fit, right? I would be the worst patient with some of those. Model doesn't fit, doesn't fit. All right. All right. So if a model doesn't fit the data, your parameter estimates may be biased. That's another way of saying wrong, inaccurate. Right? Standard errors may be biased. We saw this the last time when we changed from last lecture, last week. When we fit the model, when we had the sum score, we had too low of a point estimate of the regression slope and too big of a standard error. When we compare that to the model with the measurement model, the factor analysis in it, right? So that's what I'm talking about, right? So when you put those two together, inferences. What are inferences? Your conclusions about your hypotheses, like why you're doing the analysis. So you get into this crazy world where model fit is almost imperative. And if you want to think a little bit. Uh-oh, what we got right here? Rain. Okay. I'm looking around thinking, okay, so to those of you on YouTube, it's currently raining in Iowa City. 70 degrees and raining. Excuse me. And Erica will tell you, because I taught Wednesdays last semester, every Wednesday we had snow, it seemed like, to begin the year. So this is a Wednesday tradition. Last week we had rain, this week we have rain, but it's not going to rain on model fit here. I'm trying, pulling all the, I'm not, here's what I will do. I will do every corny pun possible, but I'm not going to sing. I know Lisa likes to sing. I don't sing. All right. I won't do any of that. It'd just be cringe, as my son says, when it comes to the jokes. All right. So we need good model fit, and model fit's our first step. Here's a funny thought question for you, though. Um, you've seen before in linear regression R squared, and sometimes people say that's model fit. Have you heard that before? In some classes, some people describe it that way. In the world of linear regression, if that were all there was in the world, then yes, that probably would be model fit because it characterizes how well you can predict things. But when you get to multivariate statistics, what we're talking about is does the shape of the data work together because we have this joint distribution we're modeling at once. And so model fit is not R squared, it's how well those circles cover the dots that I just had on the parameter. Another interesting part of this is, I understand the US economy is fueled by AI right now. I don't know if you've heard these news stories, but like if you looked at the economic news of the last few months, like if it weren't for AI spending, our economy might not be in a good spot right now, right? And all these AI models, not all of these, but if you think of a certain context about AI models where you're making predictions of multiple outcomes at once, most of those do not concern themselves with model fit like we do. That's a weird difference, but those models are path models, and that is something to think about. So, an interesting interplay between what this technology, the 1900s, used to say, yes, the 1900s, that's what the kids call it now. We're from the 1900s. Um, had investigated issues in model fit much more than our AI robot overlords have now. And that's part of the interesting weirdness of it. Anyway, so we got to have model fit before we look at our results. Otherwise, our results may not be right. But just because you have good model fit doesn't mean your model is good overall. Model fit's your way of saying what's in the model versus, yeah. So, for instance, if you had data where there was truly zero correlation between variables, model fit for the model I fit with the zero correlation or the zero covariance would be perfect, right? But the variables themselves, there may not be much of a story to tell. Yes, these variables are independent. The end, right? That happens occasionally. A lot of our measures, a lot of the things we do in education, at least, are highly correlated because they all involve individuals, and individual differences plays a big role in that. But yes, just because the model fit is good doesn't mean the model result is informative, or I don't know what the looking for. The result you're looking for. It's not like you've just made it there. Model fit's just the baggage you have to get through, or the hurdles you have to jump over to get there. Questions so far? Okay. So there are different types of model fit information. By the way, everything I say here, I will repeat again in the factor analysis unit that we do after this. It's the same. So this is your first introduction. These were my original slides. I will repeat it because it's important, and I will use Lisa's slides to repeat it. You can all pick her slides as being better. I'm okay with that. That's how it works. Right? This is just who I am. I'm okay with who I am, really. I have a lot of nice attributes, okay? No, I'm just kidding. There's a lot of information on all these slides. Oh, good. I'll take that. I'm not going to tell her that. She'll have to watch it. She'll have to look at the YouTube transcript. So those of you on YouTube not hearing this, my slides were just complimented slightly. Did I summarize that okay? Okay. Just making sure I'm accurately reporting. This is Jonathan Templin reporting. That's right. I might be auditioning for 70 degrees and cloudy here in light rain in Iowa City report. I'm hoping to get that new career in broadcast journalism, yet another dying field. Anyway, I'm sorry. I love. By the way, yes, I love the Weather Channel. Yes, I put it on in the background. Yes, the reason why I love the Weather Channel, two reasons. I like maps and I like data, and they present both. The end. Right. And yes, second to that is CNBC when the stock market's rolling because I like the data on there too. Yes. Anyway, too much. So model fit, what I'm going to talk about are when the outcomes in models are what we call conditionally multivariate normal. Conditionally multivariate normal, that's a little bit to unpack. Conditionally means we have predictors for each of our outcomes, right? Because the assumption when we have a regression line with predictors is that the outcome is, once you condition on the predicted value, condition on the value, it means what's left over is normal, right? So when we have this situation where we're assuming this multivariate normal, um, all of these, there are several types. You saw the reams of output. We'll go into that. But each is based on the premise that a model mean vector, like the set of means, and the set of variances and covariances, must fit as well as that from the saturated empty model. Okay, does that make sense? So what that means is when I talked about the six-dimensional multivariate normal distribution, where we had six means, six variances, and six choose two covariances, every model that we would fit to this data will actually be nested within that. Meaning every one of the path models that you could form, they change the permute the arrows, change the direction, change all that. They're all within that big multivariate, six-dimensional multivariate model. So the comparison we're making is how well do we recreate all the data if we didn't put a model on it in the first place? That's that comparison. Most will. Yes. Not all. Yes. Yes. Yeah. And actually that's the weird thing. What I'm getting toward is basically everything in output from here all the way down to there. That's how much model fit information we get without asking that much of it. And after that, we get down here. Most of what you see in this output are model comparison measures. Actually, everything is a version of a model comparison measure. It's just the question you have to ask is what model is it being compared to? And it's not as complicated as in practice, I think, as it is when you're learning it. How's that sound? Because when you're learning it, certain statistics, I'll just pick one. RMSEA. Ever heard of RMSEA before? Of approximation. Yeah. Not be confused with the root mean squared residual or, yeah. Anyway, that thing has one comparison model, but something called the Tucker-Lewis index may have a different one. But when we look at our output, we want Tucker-Lewis to be high, we want RMSEA to be low, and that's how we sort of evaluate it. So once again, to recap, when we put a model on, when we go specify a model, this six-dimensional model that I showed up on the screen here, if we wanted to think about it, six dimensions, again, six means six variances, six times five, 15 covariances, if I'm not mistaken. So that would be 27 parameters. Okay. We have six residual variances, we have six intercepts, and then we have all these red paths. We don't have 27 parameters. So what that means is this model is an approximation to those 27 parameters of the distribution. Right? We're approximating the way our data look by the parameters of this model itself. That makes sense. That's what model fit's all about. Yet again, Law and Order hit my ear. All right. So indices, what we're going to show some first, I'm going to show a few of these model fit statistics. Model fit indices is what we sometimes call them. Are called global. These are global model fit indices, meaning how well do we fit that six-dimensional model in total. This is to be compared with, when we get a little bit further on, what we call local model fit, meaning how well are we fitting a model for a pair of variables, right? How is that covariance between performance and usefulness being captured, right? So global is everything all at once, everything everywhere all at once. Is that the movie? Right, that. Whereas local is just a pair of variables, generally speaking. Yes. In a sense, yes. This is actually slight. It's yes and no. Oh, sorry, you're not wrong. What this is, the question was, is this so? Your question, just to rephrase the question and make sure it's on YouTube. Um, your question was, is this trying to understand how much error is in our model? What I would say the answer to that question would be, we could answer that by looking at our variances themselves right here, because that sort of gives us how much a total. This is an empty model, so this is how much variance a variable has without being explained. Whereas what model fit is telling us is how far we're off. Again, what you could call error. That's why I'm saying yes and no. But how far we're off in a distributional sense, not just like here. Let me put it this way: this variable right here. These variables talk about how much these vary in general, whereas model fit will tell us how far we are off from all the variables all at once. Right? Or better yet, how those circles that I had on the graph before, how well they captured the trend of the scatter plot of the data. So it's a hard question to answer, surprisingly, but I like it. I come in here like the younger version of me comes in here and asks me your hard questions. I'm gonna. It's like a personal point of pride. Now I'm older. I'm like, God, I don't remember that. No, no, I want the hard question. If I want to ask you hard questions, you better believe you better ask me hard questions. All right. What was that? You don't want to be a data scientist? Is that what you said? Fair, fair, fair. But can I just say, hey, psychometrician, could be that. No, I know it's good. It's good. The world needs you in what you choose to do anyway. So let's do this. So we can compare and contrast, right? There are actually versions of models that exist that you would talk about in a different class context. And this is my attempt to connect path analysis with what you would do in a multivariate statistics class or in a mixed models class. So like Lisa's um, multi-level modeling class, whatever, either it's longitudinal or clustered. Um, what we have is every parameter estimated. So we call this a saturated model. It's another term, right? Not only is it empty, meaning we're not predicting any of the variables, each one of the possible 5 parameters is in the model, so it's estimated. So we've saturated, which means this will fit the data perfectly, so long as our data are multivariate normal, which we have to assume to make this analysis fly. So saturated, the one thing you want to note about saturated, pretty much everything we start with empty model will be saturated, and that's perfect fit, always. Okay. Next, there is a version of this model called variance components. A variance components model would be what would happen if you took these 2 variables, stacked their data up into a big long column, and ran your basic LM function, their linear model, where you predict which outcome is dummy coded, right? So you would get a different mean for each, but there would be one residual variance. It's a pooled variance estimate, and there's no covariance. And you're saying, Jonathan, why would you even do that? You're right. In this class, we wouldn't. This is me attempting to connect it to other things you may learn, right? This is like ignoring any dependency in your data whatsoever. But we don't do that here. There is another version of this called an independent variables model where you're estimating each variance, but not estimating the covariance, right? So let's just actually do some accounting. Saturated model had how many estimated parameters? Do you remember? 5, right? How many estimated parameters are in the variance components? 3, yeah. 1 that's shared, and then each separate mean. And I actually I'm making a distinction. The mean vector is always saturated. It's what we're doing with the covariance matrix that's not. So independent variables then has 4, a separate variance for each variable and the 2 means. And then there's a model called compound symmetry. Compound symmetry you may have heard of in repeated measures analysis of variance. And again, trying to connect this to things you may have heard of before, repeated measures of analysis of variance was the very first measures of analysis of variance, 1930s, 1940s, especially 1960s when we started teaching it much more didactically. It assumes one variance and a common covariance between parameters, right? So it actually has 1, 2, 3, 4 parameters in it. So now, depending on which class you were taking, right? This is 41, no, 62, 43. Sorry, I don't even know the number. It's like I'm deciding to move on and I've already forgotten all the numbers. So yeah, a lot I forget this semester. This is going to be a lot of fun. That one is intermediate statistics, right? That's if you just only knew how to use linear regression. This one is also intermediate statistics, like you did 2 separate analyses for each variable. And then this one is if you did the very first part of multivariate statistics or repeated measures ANOVA itself, maybe in design of, I think you talked about repeated measures in design of experiments, if I'm not mistaken. But I don't even know the numbers anymore, so just don't. I'm gonna, yeah, a short timer here. Okay, so most structural equation models, most path models, will keep the mean vector saturated. So why this matters is to achieve model fit, we need our models. So think of this as, I think Lisa would call it your answer key. Right? This is the right answer. This is where model fit is. So if we were to compare the model fit of each of these other, a little bit more limited models, we need the mean vector to match the mean vector, and we need the covariance matrix to match the covariance matrix. So it's in most of the models we run, Turns out the mean vector is a forgotten entity because most of the time it will be saturated, right? It's the covariance matrix that causes all of the difficulty in model fit, usually. Now, that doesn't, there are some nuanced models or some nuanced use cases where that may not be the case, where you may have to look at that. I'm just saying that now. Most of what we do from here on out, we're like, all right, where's our misfit? Right? And you can tell, right? You can look at this. Here's our answer key. How does this map on? Oh, it's too big for the first variance and too small for the second. In fact, it's actually a pooled variance between the two, and the sample size is equal, right? So it's 136, I believe, would be half of the sum of these. Right? So the average variance. No, not quite. No, not quite. Yeah, not quite. Not quite. Never mind. Yeah, I got too cocky. I thought too much of my ability and lost it. Independent variables, a little easier to tell. Yeah, the mean vector, it checks out, but we're off on the covariance. And for compound symmetry, yeah, we still have the same, roughly same discrepancy of the diagonal, but we're much closer on the covariance. Right? So you can start to see where that works. If you want to see model fit options in Lavaan, you have to, in the summary statement, put this fit measures equals true statement. If you don't want to see all the model fit, if you want to pretend you're running an AI model on this, sorry, I shouldn't say that. I'm going to poke at the data scientists. If you want to go put your head in the sand like our AI overlords do, no. Then you turn off the model fit and just look at R squared. All right. So that is here in this fit measures equals true. And you'll remember, if you remember using summary to look at your linear model in R before, uh, it doesn't have a fit measures option. That's because when you install Lavaan as the package and you give summary something that comes from a Lavaan model, it allows it as an option. Right. So some options there. Yeah. Right. If you just do this right here, output's a lot shorter. Right here. I don't need to do anything differently there. N- no, the fixed x equals true is actually relates to how it handles variables that are exogenous, whether or not they are part of the model likelihood function or not. And so that's a rabbit hole we'll get down in a few slides. Okay. All right, going back to the slide here. All right, so there's the output. All right, so let's go through that output section by section. That's what this is here. We'll start with the unlabeled section right there. And actually, let me recreate the output here. Here we go. The unlabeled section up top right there tells us the estimator is ML, in this case, maximum likelihood robust. Uh, I don't even know what that means. NLMIND, that's an optimizer that tries to give us a parameter estimates in maximum likelihood. So again, unlike least squares like regression, we're trying to maximize a likelihood expressed to the functions. The most important thing here is the number of model parameters, though. That is a way of checking that your model should be right. We just did a quick accounting of our path diagram, and I said, oh, there's possible 27 parameters. How many do we have? These are the breadcrumbs of making sure that what you specified in Lavaan work, right? So check those number of parameters. Um, Also check the number of observations. There are 348 that we use out of 350. That's because two individuals had missing data for both scores. And in this analysis, when they both have missing data, there's nothing you can do to remedy that. Basically, it omits them because it's like they didn't show up at all. Okay, that's our unlabeled section. Actually, this is slightly out of order. Likelihood ratio test versus saturated model is really what we're talking about here. That's this. Actually, sorry, I should change my slide. They labeled it model test user model. And here, you'll note this test statistic. So what this looks at here is Test statistic, I'll get to that in just a bit. Degrees of freedom, that is the difference between the number of model parameters you have in your model and the number of parameters that are in the saturated model. Right? So remember what saturated means. Every parameter gets, it's the answer key. You estimate every parameter that's possible. And in the saturated model, we saw there were five. There's two means, two variances, one covariance. Well, in this model, we've estimated two means, two variances, one covariance. So we get a zero here. When you see a zero for degrees of freedom, that will indicate to you that the model fit will be perfect. Because there is no way, basically, you have recreated that multivariate normal distribution perfectly. In fact, when you generate the model implied covariance matrix, it will be perfectly spot on to your covariance matrix in your data. Actually, right. That's basically it. Well, another way of looking at it is when fit is perfect, you've already checked the model fit box. And there are occasions, both in path models and factor models or measurement models, where that will happen, right? It's particularly common in path analysis because if you think about model fit from a, like when you were in intermediate and you took linear regression, there was no model fit. It turned out it was a univariate normal has two parameters, a mean and a variance. The model for the means always saturates the mean, and you have a residual variance saturating the residual variance. You didn't talk about model fit at all from this context. So here, when you see zero here, you'd say it's perfect model fit. Therefore, you wouldn't even report any statistics because they're all going to be at their limit for what good will be. Yeah, it may. Yes. Yes. Ah, yes, it does. And so this is where I wanted to show the difference here, right? Actually, you all are with it more than I am today. Some good questions. This is what it looks like when we did it. So this model here is a model where I've constrained the variances to be equal. This is the compound symmetry version, right? So the variances are equal, the off diagonal, there's only one that's estimated. So there's only four parameters in our model. And here what we'll see is there's 1 degree of freedom. So that means our model had four. There were possibly number five out of a possible five parameters. So we had four out of the five. Now, Levon, that's what this right here is, should be model O three's output right there. There we go. So in model O three, now Levon reports this weird. It says we have five parameters with one constraint, but that means we've only estimated four. Yes, Levon has iterated on how that has appeared over the years. Um, with 1 degree of freedom, now we get a non-zero entry in the test statistic. So it turns out the test statistic, that is -2 times the difference in log likelihoods between your model and the saturated model. It's a likelihood ratio test. So remember, we talked a little bit about likelihood ratio test. But by the way, you're not going to need to compute all this. You don't need to like calculate it, but think of it this way: that 603.527 is as if I ran two models, right? In fact, we do have those two models. Let me show those to you, right? Here, our likelihood ratio, our likelihood model log likelihood, which is a characteristic that comes from the model itself in a likelihood, maximum likelihood sense, is negative 2085.032. Let's stick that right there. And here, our model log likelihood is negative 2386 right there. So if I do this, I do, did I get the right numbers? Yes, that's right. I need another negative right here. There we go. -2 times the difference. And of course, I changed. I did. Yeah, I always get that. There it is. Well, 603.528. Here's what I'm trying to tell you: 603.528, where it comes from. So what's happening? It actually it's equivalent to if you had run both models at once, one that was perfectly fitting, saturated, and one that was not. This statistic would tell you if there's any difference between the two statistically. So 603.527 is -2 times the difference in log likelihoods. Turns out in statistics, and why maximum likelihood basically runs statistics after you get past linear regression is because that thing, as sample size goes to infinity, this thing becomes a chi-square statistic. Under what I kid you not, they say this in statistics, and I've already missed my break. My God, under mild regularity conditions. I kid you not. That's what they describe it as. All right, that I'm going to leave you. Let's take 10 minutes, and you can think all about what that means, and we'll be right back. So, what I'm going to do for this part of the lecture is not cram it all in. We're going to take a leisurely stroll, and these slides will come back again in a couple weeks when I teach class. But I will stop lecture today about 3:10 to talk some planning ideas. Basically, I want to show you. I've already posted material for next week, and we'll talk about that. And then I'll say what I'm going to officially do with homework and changing the order of things. So I'll do that. Okay. Yeah, and then I'm saying this out loud, even though I just told you all this without it recording, because if anybody's not here, now they'll hear it. And anybody who's watching the class for fun, it's just you can just fast forward through this part, right? That's right. And if you're on the treadmill while you're doing this, don't trip. There. Yeah. I've heard people listen to the podcast like, well, exercise, not podcast, like podcasting. Yeah, I should do that. I should do that. I should exercise. There's all sorts of things I should do. Okay, going back to model fit. Okay, so once again, model test user model, global likelihood ratio test, comparing our specified model with the model where everything's estimated. This is your check on the answer key. This is the most powerful test statistic. You will probably think it's, let me see here if I can do this. My child's 10. This is OP. OP, it's overpowered. It is overpowered. How did I do, Eric? No, no. Yeah, this one right here is OP because small small differences between your model and the saturated model, the answer key, will make this thing significant, right? So this number I mentioned before, with mild regularity conditions, this thing is a chi-square with 1 degree of freedom, which means chi-square 1 degree of freedom gives us a p-value of 0. So we would reject something. What is the hypothesis test that we're rejecting here, right? Technically speaking, it's does your model fit the saturated model, right? More complicated than that, if you want to get into it, you have to think about the constraints that you put on your model to move it off of the saturated one, right? So this is, I'm not going to take a long time on this, but if you look at our model syntax here, this little command here, this word, this label in parentheses with a multiple, because it shows up on 2 lines, it is a model constraint. It basically makes these 2 parameters equal. Now, we'll return to this later in the semester. You don't need to take notes of it now. Just conceptually think it through. So this is saying that one variance, the null hypothesis here is one variance is equal to 2. That's basically it, right? Where the alternative hypothesis is it's not. So that test statistic that you see here, this OP'd test statistic, this thing is, I'm going to keep saying it, overpowered test statistic, you see a p-value of 0. Okay. Other part of this, what we would say is with this, our model doesn't fit the saturated model. That's what it's saying. The end. So a p-value low here is bad news for model fit. Now, side conversation on that. Uh, Again, trying to speak like my son does. Low key, No one looks at that part of the output. I know. I'm trying. I'm trying. Low key, no one cares about that model fit, right? Because why no one cares about it is it's so powerful. Small discrepancies show up there. So this is like the best. Now the other thing you're going to note, there's two columns here: standard and scaled. If I didn't estimate the model with the option MLR, so if you remember in this call to the SEM function, at the end of it, I had estimator equals MLR. This estimator equals MLR produces the scaled version. So in theory, what you should be looking at is this version on the right-hand side. Why I didn't describe that to you earlier is this number takes extra calculation to derive, right? Where I had gone before, as I said, oh, look, here's the two log likelihoods, -2 times their difference gives me 603.57. The scaled version is now, there's what's something called a scaling correction factor that's estimated that sort of reverts how much, what that number should end up being. This thing, the scaling correction factor, is basically trying to account for not normal data in leptokurtic or platykurtic, basically the tails not being normal of your distribution. But it's a better statistic. Like if you end up getting perfectly normal data, your scaling correction factor would be 1 and these two would match. So at a minimum, MLR gives you what you would have done already. And as an added bonus, if your data don't meet the assumption of multivariate normality from a kurtosis point of view, it protects you against it. So always look in the right-hand column. I just didn't describe that to you because it takes an extra calculation. Actually, that calculation is in my slides, and I'll quickly go to that real quick. So everything I just told you there is right here. I'll say it again. Um, it says robust. This should be scaled column over there. It used to be called robust. Now it's scaled. But the chi-square comes from the comparison of models. The null hypothesis is that this model fits equally to the saturated model. That's the easy way of putting it. I think that's preferable to everybody. The alternative is it does not fit equally to the saturated model. It's not great in small sample sizes. And in large sample sizes, again, it becomes really, really sensitive to minor deviations from model fit. So because of this, what has been created are a series of other fit indices out there, right? So we just mentioned chi-square. Here are the three different chi-squares. I did not replace these because the numbers are the same. This is the old version of Lavon, but these numbers are the same as I get in my output now. So robust is actually scaled today. They've changed the label for it. But here, the saturated model, 0 degrees of freedom, zeros everywhere, that's perfect fit. It is the saturated model. But every one of them you can tell, okay, the variance components, remember variance components were equal variances, 0 covariances. That was not good fit. The independent variables had a p-value of 0.018. That wasn't too bad. And then compound symmetry, also not good fit. Yes. No. Oh, yeah. So in this case, no. So what ends up happening for every model that you run, it automatically looks at the comparison of that model with the saturated model. Always. Always. Yep. Yeah, that's right. You'll have to figure that out yourself. Yeah, that's one. If you wanted to compare these two, you'd have to have a priori knowledge if they were nested. And if they were, then you, yeah. Hmm. Yep. Yep. Yeah, it's incremental. In that case, so the logic of this model is purely didactic. I'm saying there are these other models that exist And I haven't gotten into how we specify them in a path diagram and how that translates, but basically saying when we don't have 0 degrees of freedom for this test statistic, it means we're not saturated. That's all the only purpose of being here. But I will answer your question from a general sense. If you look at your syntax, you have to determine whether a model is nested or not. That's hard to do. Actually, as the models get more complicated, like I've been doing this a long time, I have a good sense of it. It's one of the harder things to do, be able to say this, 86 parameter model is nested in this 96 parameter model, right? It's hard to do. The way that I tend to summarize that is to say, what parameter changes do you need to make to go from one to the other, right? So if you can specify it as a function of, I only need to put zeros on one model's parameters, then they're nested. That's how I'd say it. But if you say, I've got to put zeros on these for model one, and then zeros on these for model two, they're not nested, right? Now, second, if you're in that situation, the way you test fit is the ANOVA function. And so what ends up happening is, and I think you said model two to model one, is that right? Just as a hypothetical, you can put this into the ANOVA function, and it will give you a chi-square that's scaled, but this is going to have to assume the models are nested. I don't know if it warns you. I think it warns you if it detects they're not, but it may not. But yeah, literally to compare model fit to get that same likelihood ratio, you can put this in the ANOVA function. Thank you for the question. Other questions? Yes, I know this is like so boring when you're like, just show me the model already, but this is what you have to do. You build your model and you check model fit. And then by the end of it, if the model fits okay, then you can peek at the parameter estimates. Right? It's always that way of working. Okay, I mentioned where the likelihood ratio test comes from. If the scaled version is actually this thing right here. So this scaling constant that you see is actually built from this likelihood ratio text section of the output. So getting into Levon, again, if I look at model three's output right here, the very top model test user model is your likelihood ratio test. Where the number 1.358 comes is from looking at the robust statistics and the scaling correction factor for each of the models. Your model, saturated model, and then using this formula to figure out what that happens to be for the scaling correction factor. Once you have it, all it does is you divide the chi-square statistic by it. And that's its rescaled version. That's why they call it scaled and not robust now. But again, you're not calculating this by hand. And I'm going to make a very bold statement right now. I don't want you memorizing these formulas for the exam. Okay? So there will not be formulas. Now, if there is a formula to be used in the exam, I will give it to you. Okay? But I'm not going to make you remember this esoteric formula because I can't remember it. And as I mentioned about the headstand comment, I can't tell you if I can't require you to do something I can't do myself. This is not like coaching athletics, right? Am I wrong? I mean, like how many of those coaches are going to be able to do it? Now they may have in the past, right? But many of the best coaches were not the best players. All right. So you've seen all this before. This is just the output to where it shows up. Um, so just remember, if the log likelihoods of the current model and so current model is user model, saturated model is unrestricted, right? If these two are the same, you have perfect fit, right? And that just means when you recreate that multivariate normal distribution you're assuming about the data, the parameters from your model will lead to the same covariance matrix as if you just calculated on the data itself. Okay, so that's that part. Next section, model test baseline model. Okay, it's still called model test baseline model, right here. Model test baseline model provides a likelihood ratio test that is Useless, I think. Right? Maybe back in the day, it's like a relic from when we learned how to do this, I feel like. Right? Um, it compares the saturated, so this doesn't even compare your model necessarily. This compares the saturated model with a model where the variables are independent. In this case, what we call the independent variables model. And so if you remember what model 3 was in my slides, independent variables look like this right here. So what this section of output does, regardless of which model you do, is it compares the saturated covariance and mean vector with the saturated mean vector and covariance matrix where all the off-diagonal elements are zero. So why would you need to do that, is what you might be asking. And the answer to that lies in the premise of multivariate statistics, in that if all the covariances are zero, well, I mentioned before, a correlation is just a rescaled covariance. Well, it turns out all of your direct effects are also rescaled covariances. So if all the covariances are equal to zero, that's like saying, yeah, I don't even bother. There's no correlation between any of the variables whatsoever. Don't bother doing a model. It's like you collected completely independent data in the first place. So this section of model fit, I think I spend way more time talking to you about than I ever look at when I look at my data. Right? I teach it more just to tell you what it means, but this is basically saying, okay, what's the null hypothesis here? Well, what are the constraints? The null hypothesis are all covariances are equal to zero simultaneously. Now, we only have one in this model, but if we had 50, they'd be all equal to zero. And the alternative hypothesis is that at least one is not equal to zero. We get a test statistic that is the likelihood ratio test between the two models. And of course, the second column is the rescaled likelihood ratio test. And the p-value for that tells you whether or not you should reject the hypothesis. And so in this case, our p-value is fairly small. I'm just going to if I don't say otherwise, let's just say the alpha type 1 error rate is 0.05 just to make our life easy. By the way, I've been doing Bayesian stats for a long time lately, and it's like weird to come back and say type 1 error. So we don't talk about that a lot in Bayes, even though it's sort of a premise that's still there. But type 1 error rate, this would be less than type 1 error rate. So we would say, what's this, our conclusion? It says our one covariance is likely not equal to zero, right? We would reject the null hypothesis that it's equal to zero. I don't know, again, it's not often reported. Most likely you have correlated variables. In fact, I'm going to challenge you to find variables that are uncorrelated, right? That does happen. Lisa and I, after doing this for, I actually lied. This is my 21st year teaching. I did 20 last year. Can't even count right. Lisa's at 20. And in our combined 41 years of doing this, I think we've seen 3 or 4 examples where variables didn't correlate. 3 or 4. And we've worked with lots of data sets, right? So, yeah. Okay. You can see that for each of the 4 models, this test doesn't change. Why doesn't it change? Because this test never depends on your model. This is basically testing your data, right? It's the same test regardless. It says, does the saturated model fit better than the model where all variables have 0 correlations? Those 2 models always exist regardless of which model you estimate. Right? So this is not even a model fit test for your data. This is like a test of correlation in your result. Right? But if you're looking at it saying, I can't tell the difference in these 2 sections, I can understand that. Because apart from the label that is not descriptive, the values are the same. So you have to make a note of that. The top one, the model test user model, compares your model to saturated. The model test baseline model compares saturated to independence, regardless of your model. Okay? I know, it got real quiet in here. Like, why do they do that? Why do they call it that? Well, they are getting better at naming things. So maybe we could put it in here. I believe his name is Yves, who the primary author, Levon Yves. If you are listening, which I doubt you are, but that's okay. Maybe next time label baseline model a little bit differently. You've done it better. Levon is amazing. Keep going. Anyway, there. Just not that a pep talk from some guy in Iowa City, where it's currently 70 degrees and raining, is important. Okay. Um, so next, this is actually relabeled, and I didn't realize it. Oh, no, it's not relabeled. Here we go. This user model versus baseline model now has a section. It's not quite what I described in my slides because the output has changed. As I mentioned, Levon is evolving. But the next section describes our first fit indices. There's something called the comparative fit index and something called the Tucker-Lewis index. These are just two of a plethora of fit indices. Um, Although I was alive in the 1980s, I wasn't cognizant of this field, but that was the time to be in the model fit business because there are versions of software that still exist, SAS-Proc Calis, for instance, that will output way more than this for fit statistics. It was like every person had, not every person. What we're summarizing is this complex difference between covariances in a big matrix. And so there's multiple ways of doing that. These are two ways of looking at it. These indices are where you tend to look more frequently. The CFI, the comparative fit index, higher is better. And the TLI, higher is better. I want to make one other point about this. When you see the word index, usually higher means better. This is going to be different in just a moment for another statistic. But index, higher is better. Okay? That's right. Yeah. This is where the weirdness of this works. This is basically saying how much better does your model fit over independent variables? So if you were to say, okay, saturated is our goal, and you put your model in and it's not saturated, so you want to go look at fit. So that's one comparison. These indices are saying, how well does your model fit better than independent does to the saturated? Right, that's it. And what you'll see here, so this is model 3 that is not independent variables, excuse me. And this is, model 3 as well. Let me see if I can. Model 2 is independent variables. In model 2, you'll see these numbers are 0. Why that is the case is because both of these fit equally well toward the saturated model, right? Um, yes, that's a great question. Um, it comes from an old philosophy when we started multivariate statistics, in that correlated variables are why we do multivariate statistics. And so our assumption for independent variables is there are no correlated variables, right? Why that? I struggle as an instructor. There are better people who can describe this to me. I mean, I need to figure out this better. Maybe I should go to ChatGPT. Never mind. I struggle to describe why these indices are really relevant because you're like, why do I care if my model fits better than independent variables? Because everything should fit better than independent variables if independent variables doesn't fit my data. Yes, I think this is sort of saying how much better it gets. That's the closest I can say, but I don't know that this has a lot of. I don't. I will say that since Levon and M plus have really truncated model fit to be these two indices and maybe one or two other ones, you see these reported quite frequently in empirical studies, people doing science with path analyses. So it's almost mandatory that you report them. And yes, you want them bigger than 0.95, but they get a little weird. In fact, here, um, again, here's their max. Here's their math, the math behind them, the max. That's max. What this is comparing is your current model with the independence variable model. Like, okay, so what's bigger, your current model's chi-square minus its degrees of freedom, or 0, versus that numerator, I'm sorry, the current model's chi-square versus minus degrees of freedom, the independent variable's chi-square minus degrees of freedom, or 0. Anyway, Tucker-Lewis index is a little bit differently. Non-norm fit index is what I believe they called it. This thing will often go over 1. CFI gets to 1 itself. This thing also can go less than 0. It gets a mess, right? But we tend to report it all the time, whether or not it's needed. It's just sort of mandatory these days. And as we look at them, there was a paper by Bentler and, what was it? Oh my goodness, I'm blanking on it now. Not Yuan and Bentler. Bentler and who? In 1999 that came up with sort of criteria for these fit indices. And that's what you're seeing here. Over time, model fit has gotten much more precise and evolved. We're on like iteration 12 of model fit generation these days. But most of what you see now is still the same. You take a look at CFI, you want it bigger than 0.95. Sometimes you allow bigger than 0.9. Those two criteria also apply to TLI. Right? So when you see the indices, think 0.95 or bigger is for good model fit, approximate model fit. So weird. 0.95 would be good fit. Yeah. Yeah. So um, I'm associate editor for a journal called the European Journal of Psychological Assessment. It's not a pure methods journal. In fact, it's people reporting surveys. And as associate editor, I select reviewers. I get to read their review comments. I get to put my own, yada, yada, yada. If a paper doesn't have these, not going to get through, right? You need these indices. So these are important. That's just the calculation steps behind it. I'll quit that. We move to the next section of output, which will be here. And that happens to be the log likelihood and information criteria. So once again, log likelihood, this likelihood user model H0 right here, that's your model's log likelihood. A log likelihood is basically the density of the multivariate normal for each person, logged, like the height of their data when you plug in your model parameters, right? So you can actually calculate it. This thing is yours. Then they also have that for the saturated model. So they report both. Right? It's almost as if you get a model run for free. It's like, actually, we've talked about 3 models here. Your model, saturated model, independence model, right? This is your model. This is saturated model right here. From these statistics, you can calculate information criteria. If you've never taken a maximum likelihood method before, never used it before, information criteria are what we use to compare non-nested models. Right? So basically, Michael and I have different ideas about data. I put in way too many parameters. He says, come on, Templin, this isn't how it works. Puts in a parsimonious, simple model. They're not nested, right? He says, what's your AIC? I say, it's 4184. He says, oh, mine's only 4,000. Who do you pick? You pick the lower one. So these are for comparing models that may or may not be nested. People use it for both. Technically, only non-nested because likelihood ratio is a more powerful test. Right? You compare each model on the basis of that statistic. Now, there's multiple statistics here. But what that means is, again, if we're comparing models, you say, what's your AIC? I say, what's my AIC? Oh, AIC prefers his. Great. Next, what's your BIC? Hey, maybe BIC prefers mine. Can happen. Now what do you do? Well, AIC says Michael's model, BIC says Jonathan's model. What are you going to do? And then there's another one. Same thing there, right? So each one of these statistics is used to compare non-nested models. Um, this usually doesn't apply as much in standard analyses. So if you take the path model and try to address like that paper does that we're basing this lecture on, like substantive questions, you're usually not comparing with these, right? It's only when you're like, I've got this radically cool new nonlinear whatever, and I got an AIC, and I'm going to compare that with this not so cool or standard analysis. That's where you usually see it, right? Any questions on any of these? Ugh, model fit. Okay. Oh, one last thing I would note is because these show up in the likelihood ratios test section now, although this is not an old, because the core, each one of them is formed with negative 2 times the log likelihood. So they come from what results from the maximum likelihood estimation process. Okay, I just talked about comparing information criteria. Now we get into the one that's probably referred to the most, which is something called the root mean square error of approximation. And yes, I called it root, not like my spouse. It's root for her. I don't, I'm from California. I've lived in the South, in the Midwest. I speak a few dialects of English, but it's always going to be root to me. Um, but this thing, you want to be low, be zero, right? It goes from zero up. How do you remember which one, which direction? Because we just saw CFI and TLI, we want those to be bigger. Root, we want to be lower. And I believe Lisa taught me the mnemonic that said, oh, like roots are like trees have roots and they're in the ground, they're low to the ground. Yeah, that's it. Think of that. Root. No, don't like that? Good. You want zero error. Spoken like a true statistician or math guy. I like it. I like it. Okay. This compares your model. That says CFA. That should just be your model, CFA or otherwise, with the saturated model. So this is a comparison of really what you're at. It relies on something called a non-centrality parameter, which is how far off the chi-square is. The bigger picture is this right here. Just ignore the math for right now. The RMSEA goes from 0 to 1. Smaller is better. And really, we want this less than 0.05. That being said, you can quickly go find studies where RMSEA is much bigger than 0.05, right? In fact, one of my favorite stories from this class, um, when Lisa and I were at Kansas, we used to work with people in the Lifespan Institute, her much more than me because she was actually appointed in the Institute, um, where they used a scale called the BASC, the Behavioral Analysis Scale for Children, BASC. Anyway, evidently it's fairly famous. I wouldn't know. The school psychologists love it. The guy that hired me at Georgia, the department chair, was then dean at Georgia State, created it, Randy Camphouse. So, like, cool. If you look at their technical manual, they start reporting RMSEA for a higher order model, which we'll talk about later in the class, and it's like 0.21, which is well above the unacceptable level. But that's the gold standard in their field. You got to use this test, right? So RMSEA should be less than 0.05, but it gets difficult to see. That presents the issue that we have. One justification could be, well, we've been using it, so at least we know some of its behavior, even if the math is not exactly right. So we could say, oh, it worked like this in this situation. Does it still, right? Um, from a publication point of view, if you're doing path analysis or later on structural equation model, if you're not selling a product, I'll just put it that way. The other part is it's for sale. If you're not selling a product, as I described our program, what did I describe our program? We sell thetas in our program. We sell ability estimates. We sell parameters, selling thetas. Um, if you're not selling a product, scientific review is pretty stringent on this. Most likely, you'll want 0.08 or less, right? really good fit's 0.05 or less. And where this really makes a difference is less so in actually all of these make much more of a difference when we get to measurement models than path models. So the simple reason is there's far fewer parameters in the model than there is in the saturated model. We'll talk about why when we get there. But RMSEA should be smaller. Here's the result from our comparison. So this one was 0.21. This is a model 3, I think. This smaller is better. So this is model 3. Let's see, double check. Yeah, 1.1, and actually there's the robust version over here, so 0.115. The nice thing is Levon will also give you some other details now. So you have a 90% confidence interval that it's lower. The lower and upper bounds, you can bound it, so it's 0.115, but it's somewhere between 0.04 and 0.21. And you could say, well, that's great. What's the chance it's really good fit? 7%. What's the chance it's less than 0.08? 81%, right? And then you have a robust version as well. If you're looking at all this, look at the robust column. That's more accurate. Yeah. Is the point of it is used for either interchangeably. What the non-standard, the right-hand columns are thought to be more accurate when the data deviate from normality with kurtosis. Okay, any other questions on RMSEA then? All right, this is the part of the class where I'm going to pause the lecture. Let me just make sure I don't have anything here. I'd show you how to calculate. Don't calculate it by hand, okay? That's the other thing. No hand calculations of stuff like this. Now, there may be, like, you may need to add a few numbers together on the exam, like counting parameters or things like that. So there may be a few calculations, but none of this stuff. Nothing with a square root. Nothing with a calculator needed, okay? All right. Let me do one more, and then I'll talk to you. We're almost done. All right, we're almost done. The last one is something called, and get this, standardized root mean squared residual. So the last one was the root mean square error of approximation, and this is standardized root mean square residual. And you'll see the core of both of those is root mean square. But what are you root meaning? Or what are you squaring for a root mean is the difference. But this one is probably the most understandable. The standardized root mean square residual is the average standardized difference between the estimated covariance matrix of the saturated model and the estimated covariance of your model. So put another way, this is the independence model covariance matrix. This is the saturated model covariance matrix. And roughly speaking, we're off a little bit on the diagonal and a whole lot on the covariance down here, right? So what this tries to do is it says, how far off are we in the standardized sense? Standardized, you can think of as like, what's a standardized covariance? It's like a correlation. Right, this is saying we're off by about 0.066 standard units in that sense. And what we only have one in this case. I don't have any more here. We only have one parameter we're comparing here. Where this is really useful is when you have a covariance matrix with 50 or 60. Right? This is sort of your average, how far off on the standard unit you are. Some people have seen, I've sometimes seen people say this is less than 0.08. There's also massive heterogeneity in programs for how this is calculated. So M plus does it one way. Levon, I think, mirrors M plus with the mimic equals M plus. Otherwise, it'd do it a different way. The Stata package, is it SEM or whatever it does? I think it does it a different way. Like what the units that go into it are highly flexible. But the bigger picture is you want this to be small. And imagine this, if you are estimating the saturated model, it will be zero. Exactly zero. Right? So another reason to say it. Questions on standardized root mean squared residual? Great. Well, we'll talk about all this the next time. One thing before we end, one more thing. I was mentioning before about plans for homework. I will move up here. Actually, let me go to our course website. I want to talk a little bit about next week. Next week, I will not be here in person, so you are welcome to come to class. You just won't see me here. If you need a place to watch the video, you can turn on the computer and watch the video. I have put a couple things up. First, the readings. McDonald's chapter 5 is the opposite of what you read this week. There are no equations. I mean, very few equations, no matrices. Okay? The test is about the quiz is about reliability, which you may have already seen a little bit about, and basically. So this would be in the part of the if I didn't move path analysis to the front of the class, this would be where we're getting into measurement and measurement models. And I really like Lisa's approach. This really stems from this book, by the way. That's the book I first learned this stuff from. And when I was in grad school in 1998, I started. The Rod had literally the proof pages, not even the proof pages, like the double spaced like text pages that he gave to us to go read the book. So we're reading the book before it was out. Anyway, he sort of put classical test theory, factor analysis, IRT into this one text. They did a really good job with it and building it from that premise. So that's what Lisa's really done in her slides, and I've also tried to emulate. So we get into classical test theory, which is the art of adding things up and trying to make inference of them. And she's got some great slides. You can take a look at her slides. There will be no questions on this. At a bare minimum, just read the chapter and answer the questions. But for your information, I think she does a great job with these lectures for there. And then, because we're moving into factor analysis, you might think, I learned exploratory factor analysis, or my advisor tells me about exploratory analysis, or somebody asked me to do something with an eigenvalue. One of those. That's what this lecture is about. This is describing what exploratory factor analysis was and why we really don't do it as much anymore. Now there are people who do it, but it is how do I put this? Subject to a bunch of artifacts in the best case, and in the worst case, it's another version of confirmatory factor analysis. It's just what makes it confirmatory is so nuanced that good luck describing. It would fit in David Kaplan's book, let's put it that way. Right? There's a very specific constraint that most maximum likelihood versions of this use that is really hard to describe what it means for data. But that's that there. None of this will be on the exam. Say that too. So that sounded okay. So what we will do is we will do classical test theory and EFA, and then we're going to come back to path analysis part 2 of this lecture, and we'll finish the slides moving forward with it, this lecture. Now, I'm only on slide 45, so I got another 65 slides to go, but we'll bump that into the CFA time. I think things will go a bit quicker because now that we're done with model fit, we're not entirely done with them. We still have some more model fit to get through, and then we get into standardized coefficients, but then it starts to go a bit quicker. But all of those things, especially model fit and how we remedy model fit, show up in the factor analysis and measurement models next too. So this is sort of going to be a very repetitive. So even though I'm investing time here, I'm not really bumping CFA out of the way. I'm just emphasizing the model fit portion of it first under path models. Questions from me before we head out today? I am going to, pardon me, yes, the last thing, I will switch homework. So whatever just got announced as homework 1, do not do it. You can get a head start on that if you want, but it'll be due a while from now. Homework 2, which will basically be grab some data, work on it. I'll put that forward, but I'll also make it so that it has a 2-week deadline, mainly because I need to get through this lecture before I give you the path analysis homework. So that's what's going to come up. I will do all of that probably tomorrow morning because by the end of the day today, just to get the video up takes enough time. So I will do that. Other questions? A quiz and the beginning of a homework that will be announced tomorrow morning. But that homework is basically find a data set and tell me about it. And if you don't have a data set, work with me to help you find one that is hopefully meaningful to you a bit. Okay? Great. Thank you for making my afternoon good. Really like teaching, really like seeing you here. Hey, last class at Iowa. I'm hinting on my YouTube video. Stay tuned, YouTube. All right. Take care, everybody. Yeah, like and subscribe.